So 124 light years, no one really knows what that means. That's 700 trillion miles. No one really knows what that is. It's just a long, long way away.
What if our universe isn't the complete picture, but merely a fragment of a much more expansive cosmic reality? What if the Big Bang wasn't a singular isolated event, but rather a catalyst that spawned a cosmic twin to our own existence? A recent and groundbreaking discovery made by the James Webb Space Telescope challenges everything we thought we understood about the cosmos. By gazing deep into the universe's past, Webb has uncovered celestial objects that, based on our prevailing understanding of astrophysics, simply shouldn't exist. They are too massive, too luminous, and too well-structured to have formed so soon after the Big Bang. This isn't merely a minor discrepancy, it's a discovery so consequential that it compels us to reassess our most fundamental cosmological principles. It has driven some of the leading physicists worldwide to seriously entertain an idea once confined to the realm of science fiction. Could these enigmatic objects represent the earliest concrete evidence of a second universe, a mirror image of our own that runs contrary to our understanding of time? The identification of these impossible entities is forcing scientists to rethink the very foundations of their theories. But how could this reality be possible? To grasp the enormity of Webb's findings, we must first revisit the narrative of the universe as we have historically conceived it. For decades, we adhered to a coherent storyline of cosmic history known as the Standard Model of Cosmology. This narrative begins approximately 13.8 billion years ago with the Big Bang. In the nascent moments of existence, there was no space, no time, merely an infinitely hot, dense singularity. Then a rapid expansion occurred. Within mere fractions of a second, the universe experienced a period of inflation that exceeded the speed of light, giving rise to space-time itself. As the universe gradually cooled, the laws of physics as we understand them began to emerge, leading to the formation of the first elementary particles. During the initial 380,000 years, the universe was engulfed in an incredibly hot, opaque plasma. This epoch is often referred to as the Cosmic Dark Ages. Only when the universe cooled sufficiently for electrons to combine with atomic nuclei did the first atoms, primarily hydrogen and helium, emerge. At that juncture, the universe became transparent, allowing the first light to escape, which we now perceive as the cosmic microwave background radiation. From this point, the narrative was thought to follow a slow, methodical progression. Gravity, acting as the universe's master architect, began to exert its influence, pulling together minuscule clumps of gas composed of hydrogen and helium. Over hundreds of millions of years, these primordial gas clouds were expected to collapse, igniting the first stars. These early stellar formations, massive and brilliant, would burn brightly for a short duration before exhausting their fuel and exploding into supernovae. The explosive remnants would then enrich the surrounding cosmos with the heavier elements essential for the formation of planets and the emergence of life. Over billions of years, gravitational forces would guide these stars into fledgling galaxies. These infant galaxies would go on to collide and merge over extensive timescales, steadily sculpting the magnificent spirals we observe today, including our own Milky Way. The central tenet of this entire narrative is that cosmic evolution is a slow, measured process. According to the Standard Model of Cosmology, the universe operates within a cosmic speed limit. Yet, the findings from Webb appear to have shattered that speed limit. The James Webb Space Telescope represents humanity's most advanced time machine, purposefully engineered to peer back to the cosmic dawn. What it has discovered is nothing short of revolutionary. As Webb delved deep into the vastness of cosmic time, reaching an era just a few 100 million years after the Big Bang, it stumbled upon an astonishing revelation. Massive and mature galaxies that defy all expectations. Scientists had anticipated observing faint, chaotic proto-galaxies, the nascent seeds of larger structures that would later develop. Instead, they encountered galaxies that are remarkably large and well-formed for their astronomical age. Webb has identified galaxies that emerged as early as 290 million years post-Big Bang. This discovery might be likened to uncovering a fully grown adult in a delivery room, an incongruity that raises profound questions about our understanding of cosmic chronology. For perspective, our Milky Way took over 13 billion years to evolve into the sprawling star system it is today. Yet, Webb is presenting evidence of galaxies that appeared to be well on their way to such complexity when the universe was less than 3% of its current age. Furthermore, this phenomenon is not an isolated case. The telescope is revealing entire populations of these unprecedented objects. Some astronomers have dubbed them universe breakers because their existence challenges the established timeline of cosmic evolution. Detection of a mature massive galaxy at such an early epoch is akin to finding a T-Rex fossil within geological strata that predate the existence of dinosaurs. The visual evidence is compelling. These massive structures are undeniably present, but according to our established rules of cosmic evolution, such rapid formation should not be feasible. This realization has sent shockwaves through the field of cosmology, compelling scientists to ask a disquieting question. What if the fundamental rules we've constructed to understand the universe are profoundly incorrect? The existence of early massive galaxies presents a significant challenge to the standard model of cosmology. A key factor in this challenge is the speed of light, which governs the influence of gravity. To form a galaxy, one must accumulate an enormous amount of matter, a process dictated by gravitational forces. In the early universe, conditions were akin to a thin fog of gas. To construct a massive galaxy, one would need the equivalent of billions of solar masses of this gas. However, gravity operates with limitations. It can only attract matter from the surrounding space at the speed of light. At approximately 290 million years after the Big Bang, there simply wasn't enough time for any point in space to gravitationally collect such a vast amount of material, as the spatial volume available to a nascent galaxy was too limited. This scenario can be likened to attempting to build a skyscraper within a week using only the bricks that are readily accessible from one's front door. Physically impossible. Furthermore, even if matter could be collected rapidly, the process of transforming this gas into stars is inherently slow. The gas must cool and condense, and mature galaxies typically require multiple generations of stars and overlapping galaxy mergers to develop. Observations, however, suggest that this entire progression occurred almost instantaneously, leading cosmologists to search for explanations. Some speculate potential miscalculations regarding these galaxies' masses, or propose that supermassive black holes may have formed through an unknown direct collapse mechanism, serving as robust gravitational anchors. But despite these conventional theories, none seem to fully explain the observed phenomena, prompting some scientists to explore ideas beyond our universe. To grasp this radical notion, one must consider fundamental concepts in physics, specifically symmetry. The laws of physics exhibit certain intrinsic symmetries, with CPT symmetry representing charge, parity, and time being a particularly crucial one. This theory proposes that if one were to swap every particle in our universe with its antimatter counterpart, charge, reflected in a mirror, parity, and reverse the flow of time, the resulting universe would adhere to the same physical laws. Initially regarded as merely a mathematical curiosity, the concept has evolved into a more profound inquiry. What if the Big Bang did not generate a single universe, but rather two? This idea underpins the CPT symmetric universe theory, which posits that our universe is one of a pair. The counterpart is an anti-universe, a perfect mirror extending in the opposite direction from the Big Bang, where time, from our point of view, appears to run backward. In this framework, the Big Bang is not viewed as a definitive beginning, but rather as a moment of reflection. This intriguing theory addresses several significant puzzles simultaneously. It establishes a natural arrow of time and resolves the mystery surrounding the apparent absence of antimatter. The Big Bang should have produced equal parts matter and antimatter, resulting in their mutual annihilation and leaving only light. The CPT symmetric model accounts for this discrepancy by positing that all the antimatter exists in its own universe. Together, the two universes are perfectly balanced. Although this concept has remained a compelling yet untestable and speculative hypothesis for decades, there may now be emerging possibilities for verification. So how does this speculative theory about an anti-universe relate to the very real galaxies we observe? The connection is largely hypothetical and involves dark matter, the most enigmatic substance in our cosmos.